So, Professor Alan Baker, thank you very much for joining us. And if you do get the opportunity to watch any of the other episodes that we've been putting out, you'll notice that we try to cover quite a broad range of topics. So one day we might discuss the politics of any given country or a crisis that's receiving not very much or a lot of media coverage. And then we'll just change tack completely and delve into some radically new, potentially game-changing environmental technology. So, for instance, mining the earth for precious minerals by planting trees, which is probably the most detail that I'm qualified to go into because I'll very likely get it wrong. So if you can maybe start off with a bit of background in your field and talk about this very new and very exciting development. It sounds like in both industry and in agriculture.
Thank you very much, Sam. It's a pleasure for me to be able to join you today and to talk about the beginnings of a technology. And I say it is still at the beginnings, but the beginnings have been going on for something like 30 years. And so I've got to unwind a bit, I think, and just explain how things started and where they started. For me, certainly, I'd had a long interest in the relationship of plants to metals and the resistance that some plants can evolve to metals which are toxic when they're present in the soil. Things like lead, zinc, cadmium, nickel, chromium, manganese, and so on. And that interest really led me to a lot of contact with two chemists, analytical chemists in New Zealand in the 1980s, and a long time ago now. But we had a group there together, a great range, but who met every year and developed a program of work to look at plants which grew on soils which were enriched in metals, because they had a similar interest to find out what the metals were doing in plants. And I had an interest in how they'd become resistant. And what came out of that was a knowledge that some plants can take up extremely high concentrations of metals from the soil. And by extreme, I mean probably at least 100 or even 1,000-fold higher than plants would normally do or normally survive in. And these plants became known as hyperaccumulators because they can accumulate such extreme levels of metals without showing any signs of toxicity. Normal plants would keel over at that sort of concentration. And the interesting thing is that these plants were found growing on soils which are naturally rich in those metals. So soils that were not polluted as such, but enriched in those metals. And all around the world, there are surface soils, largely resulting from the weathering of minerals, which are enriched in metals. And they provide a very unique environment for plant life, because plants that can tolerate that will grow there. Plants that cannot tolerate it clearly won't. So you get unique plant communities developed of plants which are tolerant and which also, in some cases at least, can take up large amounts of metals.
How common is this in nature?
Well, it is not a common thing. It's a rare phenomenon, actually, and the plants are endemic to those areas. They are only found generally in those areas or where those areas are repeated in the soil conditions in other parts of the world. And that is the interesting thing, that clearly they have evolved in a unique environment, and they have adapted to that by both being tolerant and also some taking up the metals. Now, the high level of metal in the plant may not be an obvious adaptation, because what can happen, in fact, is that plants can exclude metals. And that is the commoner mechanism that they seem to use. They don't take them up to the tops anyway. They might keep them in the roots, but they just don't take them up. And we call those excluder plants. Accumulator plants are those that allow metals to get in, and they deal with the problem internally. So what they're doing, in fact, is detoxifying the metal and allowing that to go up to the top, and there they build up in concentration. And these are the hyperaccumulators, which are a fairly rare group. Now we know something about 700 of them globally, which are true hyperaccumulator plants for a range of metals, heavy metals in particular, right through from, as I mentioned earlier, zinc, cadmium, lead, copper, cobalt, nickel, chromium, manganese, thallium, interestingly, some quite rare elements. And now we also know for rare earth elements. We've found that there are plants which can actually take up and accumulate rare earth elements, which obviously are elements of particular interest in technology at the moment. So they are fairly rare plants. But anyway, the work that was done in those initial years was really defining what was going on around the world. And then the idea came that perhaps we could utilize that property of accumulating metal to strip out of surface contaminated soils. So taking the plants which grew in these naturally enriched areas and then growing them in soils which have been contaminated by man. And many agricultural soils, for example, are like that. They are surface contaminated, often through fertilizer application, where metals have been added because there were contaminants in the fertilizer. And also, of course, from industrial waste application, from sewage sludge application to soils, and also from deposition around areas where metals are being processed. All of those types of areas where the surface soils have become contaminated within the rooting depth of most plants. Clearly not on spoil heaps and so on, which have got vast depths of soil where a plant could get no access. So we set up some trials using plants which occurred, as it happened, in Mediterranean Europe, which we knew took up large amounts of metals. And we tried these on surface contaminated soils in this country, which had been contaminated historically. And we found that these plants would do the same tricks when they were put on agricultural soils like that and grown more or less as a crop. And so we had a hyperaccumulator crop we could use to strip out metal from the soil. And that led to all sorts of interesting opportunities, but there was a recognition that these plants grow in natural conditions, often in very sparse populations. So making them into a crop creates another set of problems, because you're growing plants close together. They may have pathogens, for example. There may be a problem of fungi or insects, which would have to control agriculturally. So they need managing under those conditions. Anyway, we found it worked. We tested it originally with zinc and cadmium, and we could take out substantial amounts of metal from the soil and gradually reduce the levels of available metal in the surface soil. Not totally. And at that point, there was a lot of excitement. And this, I'm talking about the 1990s now. A lot of excitement then, because you can imagine the general thought that you get a bag of seed and you can put it on, and there you are, you can clean a soil just like that. Not so, because the recognition of the simplicity of the approach, I think, took immediate impact. And then everybody wanted bags of seed to grow in their garden, you name it. And the mistake, unfortunately, was that nobody seemed to appreciate it's a time process, and that you need several generations to even show a serious amount of uptake from the soil. So there is a limitation. And I think that recognition led to a lot of people losing interest, if you like, in this as a possibility. But there was continued interest in the USA. And then there was a very good consortium developed between myself, the group in New Zealand, and a group in the US Department of Agriculture to set up some very large-scale trials on naturally enriched soils with nickel. Now, nickel is a ubiquitous element in the environment because it occurs in a certain type of soil developed over a certain type of rocks, referred to as ultramafic rocks. These are naturally sedimentary rocks, which are enriched in nickel, manganese, chromium, and sometimes also cobalt. And there are vast tracts of these types of soils around the world. So they're globally of interest because they are obviously a source of nickel, which is in great demand as an element. And around Mediterranean Europe, there are a lot of plants which all within more or less in the same family, all in the cabbage family, the brassica family. And it is interesting that the cabbage family seems to have been one of the ones, at least initially, that we knew about, which had a large number of representatives of hyperaccumulator plants. And there are several genera of plants in Europe which were growing in vast tracts of ultramafic soils, these naturally nickel-enriched soils, and which are hyperaccumulators. So what they were doing, in fact, these plants were taking up something of about 1 to 2% of nickel in the dry matter of their shoots. That doesn't sound a large amount, but given that they're taking that up from probably something like 0.1% or 0.01% of total nickel in the soil, a matter of 1,000 parts per million or something like that, and they're accumulating to percentage values, you can see the sort of magnification factor. And the interest value came that if you take those plants and you ash the dry matter, you end up with about between 20 and 25% of nickel in the ash. So you're going from parts per million, 1,000 perhaps parts per million in the soil, to 1 to 2% in the dry matter of the plant. And then after that, in the ash, you're getting 20%, say, as a maximum of nickel in that enriched ash. So the plant becomes a bio-ore.
And what kind of volumes of these metals have been able to be demonstrated so far? Because obviously the main concern will be commercial scalability.
Exactly. And this is why we had a hook up with the people in the States who carried out work both through venture capitalists who were very interested in this commercial option, and also latterly with one of the big nickel mining companies, Inco, in the States. And we used plants which had been collected from Europe. These had been collected mostly from Turkey and Albania, plants which we knew took up these amounts. And these were grown in large quantities on the appropriate soils in Oregon. And we had big areas of land there where we could scale up, if you like, what we knew from small plots onto large scale, and to take the idea that this could become harvestable nickel as a crop, whereas where you would take the biomass and then you could use that biomass, which containing 1 to 2% of nickel, ash it or put it straight into a smelter and get the nickel back out. And so we had this process developed, and it was patented as a process because we were getting somewhere between 100 and 150 kilograms of nickel per hectare of land from that source. Now, bear in mind that that source of nickel would not normally be accessible because it would not be economic to mine that. You need very, very high concentrations, percentage amounts of nickel in an ore to smelt it, to make it a commercial process. And so, if you like, this is icing on the cake. This is not mining as such, but it is a way of retrieving and getting extra that you can put in. And at the same time, of course, it is progressively cleaning a soil. So you've got these were essentially agricultural lands again in Oregon, and the same in California. There are vast areas of this type of land. And also, as I said, we had that type of material in Turkey, Albania, a lot of the Balkans, a lot in Spain, Greece, and so on. So that process we patented. There was a lot of interest, and then sadly, the venture capitalists decided to try and test this out in other places using the plants that we had there, growing them in quite inappropriate environments. They took them to the tropics, and Mediterranean plants from arid areas don't like growing in the tropics. There's no doubt about that. These are plants which live in a very dry soils, very deficient in nutrients, completely different soil environment and aerial environment. And they failed badly. And so, again, there was still ongoing academic interest because we were trying to develop the technology, and the group in the States had actually improved the plants to optimize their uptake, which is the approach that we saw by using traditional plant breeding, not by genetic modification at that stage, but by actually taking the plants, looking at the ones which were the highest amount of metal, had the biggest growth, and breeding from those to get a super plant, if you like, from that. And we came up with some strains which were ideal, I think, for cropping on that type of soil. So that is where things went. And then the renewed interest, I think, came because we understood the processes much more. It's taken us a long time to understand how the plants are accessing the metal, what's happening to the metals in the plant, and which plants are showing even more extreme characteristics than we knew about. There's also a big change in technology. We've been able to get away from the standard chemical analysis of plants, using more modern techniques now of X-ray fluorescence analysis to identify metals in the plant without actually even beginning to destroy them. So we can measure what's in a plant in the field, and we can find plants which are high in a metal and which are low. We can even check the soils using this type of instrumentation. And these are handheld instruments now. So we've got wonderful new tools, I think, to do that. And that's led us, and particularly the group at University of Queensland, Dr. Anthony van der Ent and his team there, where we've been able to add to this list of hyperaccumulator plants simply because we've been able to test a lot more plants. The other way we've been able to test them is by going to plants which have already been collected. And there are a lot of herbaria nationally and internationally where we've got a lot of plants with all the information as to where they've been collected. We can use our instrument now to actually test those materials without even destroying them or touching them. So again, that's given us a great possibility for screening for the properties that we're interested in. And that's really given this boost, I think, to a lot of international interest now in looking for plants which are doing unusual things.
Perhaps some examples of plants that you're most excited about and the relevant minerals and where in the world
Certainly.
These plants are found.
Well, no problem about that. I think the most promising plants for developing are those which grow all the year round. So if you like, they're continuously accumulating metals rather than those which have a seasonal uptake. And that's why we look to the tropics. And also the tropics, of course, tend to have a very different type of vegetation to the Mediterranean plants that I was talking about, which tend to be shrubby, and they do grow quite fast on the sniff of an oily rag, but that's not the point. You know, they have a very different growth form, and they may be appropriate for that kind of environment to exploit. But in the tropics, at least we've got continuous growth and fast growth. So we looked, again, resulting from a number of interesting observations and expeditions that were being carried out. we looked for plants which are of great interest. And I was lucky, I worked in the Philippines for a while, and with a group of people interested in these types of soils. And we discovered a plant on one of the islands there, in the island of Palawan, which is one of the, probably the most westerly of the Philippine group, where there are a lot of these ultramafic soils. And we found this plant, which was quite a tall shrub. And when we tested it in the field, and we had a field test then, which is a very simple test using a chemically impregnated filter paper, which gives a color reaction when there's a lot of nickel. And we were able to test plants in the field by squeezing leaves against these test papers or any other part of the plant where you could get moisture. And we discovered there one plant which, if you cut the stem of it, we did this quite by accident, it bled a bright green liquid. Now, that led to a lot of excitement because a lot of the compounds of nickel are green colored, blue-green. And by golly, did that give a sharp reaction. And when we actually did the chemical analysis, we had up to 10% of nickel in that liquid. That showed that the plant, in fact, was taking up so much nickel into its sap, it was coloring it. And there had been one plant in New Caledonia, one of the tropical islands off Queensland, French island, where again, almost all of the island is ultramafic, huge areas of ultramafics, and it had been mined for nickel. In fact, the island was producing about a third of the world's nickel at that time. There was a tree discovered there which took up even more nickel than the one I mentioned. And it had a bright blue latex that came out when you cut the stem, and there was 25% of nickel in that. So these things confirmed for us that we're looking here at some great opportunities in the tropics. And although, again, some of these plants are quite rare because they're growing specifically, in the case of New Caledonia, that tree is endemic to the island of New Caledonia. So you can't go planting that around the world. But what we did discover, or Anthony van der Ent discovered, that the plant that I'd found in the Philippines grew abundantly in Sabah, in Borneo, on the same types of soils. And not only did it grow as a shrub, but it grew as a tree there. So it's had a lot of size. It had the same capacity, in fact, even more than the one I found on the island of Palawan. And that led to a lot of looking at other trees there, and a lot of new discoveries were made around Mount Kinabalu in the national park there. So that led us really to think about the development of what we'd thought we'd actually tested in the States by mining surface soils there, using plants which were shrubby and which could be grown seasonally, to look at the possibility of growing tree crops on some of these soils and clearly getting hold of nickel from those soils. And this is where the whole idea of what we started as phytoextraction became phytomining. And then when this was developed on a larger scale and in a more complete scale, it becomes an agricultural process. And the French group who had been working with us had renamed this agromining because it's a complete cycle. So there is a lot of interest, I think, in these plants, and they're growing now in Sabah. We've got areas there which have been developed by our French partners. We're in conjunction with the University of Queensland, which are developed from these plants which we first recognized in Borneo. And we are getting some really exciting values of nickel coming from the soil there. These are soils which are quite deep. They're developed over the ultramafic rocks. The nickel that's in those soils is quite readily available to the plants, so it's not locked up, if you like, in the soil. Plants can access it, and we're getting very good returns, something of the order of 300 kilograms per hectare of crop. And again, that doesn't sound huge, but bear in mind that this is again a bonus. Not only that, the plants taking up into their biomass can then be ashed, as I mentioned, as the process, and the ash extracted for the nickel. That side of the process has really been developed in France by chemical engineers at the University of Lorraine in Nancy in France. They have developed a very sophisticated way and very simple way, actually, of getting the nickel out of the ash. That is a very, very simple process now, but the interest is that the nickel that is produced that way is of extremely high purity. So it is not contaminated with other metals, and there is a need for that kind of nickel. There is a niche market, if you like, for that kind of nickel. It's the product is something called nickel ammonium sulfate, which is used a lot in glass making. It's used in plating, nickel plating. It's used where quality of nickel is required to be very high. So it doesn't detract from the mass requirement of nickel for other processes, but it does provide a niche market.
Right, because the sense of what I got from some of the commentary was that, oh, this will be a way to make the mining industry green and effectively end the environmental destruction that it is so much responsible for.
Of course. Now, that is the interest value that the industry would have, because they can fly the flag. And I'm not detracting from that, but there has been a recognition that this is another process that can be used. But it is never going to, I think, allow the quantities of nickel that would be required continuously in industry at the moment. The price of nickel, the world price of nickel has fluctuated a lot. And now there's a lot of demand for it because it's used still in many industries. And it's something which, again, I think is going to be a driver, the price of nickel.
And perhaps the fact that, as you point out, that the mining industry or the mining corporations don't need to fear being undermined by this process may make it easier to be accepted. And perhaps particularly of great benefit to smallholder or small landholders in otherwise pretty underdeveloped parts of the world. Can you maybe comment on that? Yeah,
that is precisely the way we perceive this. We set up a lot of work, or a lot of work was set up in parts of the Balkans, in particularly in Albania, where these soils are prevalent over a lot of the country, and they're agricultural land that is very unproductive. And the level of poverty and farming and so on is extreme and excessive. In fact, the poor farmers can't grow crops simply because the soil is so rich in nickel and other metals. It's very poor in nutrients and everything else because they're these types of soils. And so we perceived it as a way of putting some value back in that land and giving some opportunities for farmers to actually get an income from that land. And it's something that's been working for some time at a low level, I have to say now. And there are political issues certainly about this in some countries, but the principle is there. And the same thing in Malaysia, because as we all know, there's been a very serious issue of trying to grow oil palms on every piece of land throughout Malaysia, Indonesia, and so on, because of the demand for palm oil. And again, horses for courses, as we say, you cannot grow those trees on this type of soil. But it's been done. People have been trying to do it, and of course they fail. And there's a lot of failed land. And this is the ideal type of land for bringing in the tropical tree crops that I mentioned, which will grow on there, and the shrubby ones. We don't even have to have just one. We can mix them. We can have a tiered system, with trees and smaller trees, if you like, bringing back some native materials onto that land, and again, for local farming interests, and to bring value back to the land.
Well, that was going to be my next question, which you very perceptively preempted, how this would factor into an agroecological system rather than just having, like palm oil, just another monocrop.
Exactly. I think that recognition is there now, and the opportunities are there. But again, in the right environments with the right plants. And I think it's critical that we look at native plants for those areas, not to bring in materials from outside because of the complications, particularly of CITES transfers. The movement of alien plants into environments is a serious issue. And this is something that I think is going to always be there, because we're very concerned now about the biodiversity of areas and how that needs to be recognized, that we need to have local materials. So I think what's going on in Malaysia at the moment, these large-scale areas which are being developed, with the group in France, they're actually managing this, and there is a company that has spun out of the University of Lorraine called EcoNic, which is developing this in the tropics, and are actually planting up some large areas of land which have been acquired and are being managed by local people. So this is the move, and I think the mining industry has recognized this and sees this as of course, a secondary source of materials, but also I think there is a lot of benefit for them to be seen to be doing green work, if you like, as you mentioned earlier. So there's a public relations exercise, of course, but it goes far beyond that. I think it's something which is also restoring native vegetation on land, and respecting the biodiversity interests of that land, and developing these eco-cropping, if you like, or whatever you want to call it, at the same time.
Well, one of the most afflicted regions of the world that probably comes to many people's minds is the Congo Basin, which is obviously of huge importance for cobalt and no doubt numerous other minerals.
Sure.
Would this potentially be, if not a solution, to so many of the sources of conflict and corruption and poverty there? Would it?
Yes.
Would it help, do you think?
Well, yes, I'm pleased that you mentioned the Congo, because it's somewhere that I have actually worked. Again, going back quite a long way, there is a unique vegetation in the Congo, because they have, well, all sorts of vegetation, but in Katanga, as it used to be called, that region, it was the area of the greatest copper resources we have in the world. Belgian Congo, as it used to be at that stage. And the copper and cobalt occur together there, as you mentioned. And the copper is quite surface mined in many places. And the copper has been recognized as having a very powerful effect on the vegetation. And in fact, the geologists who were prospecting for copper there found it because the vegetation had clearings, because of the toxic effects it had on many, many plants that were growing in the area, but not resistant to copper. And so the vegetation developed in Katanga, as it was, or is now again, I think, has a unique flora. And it's been very well studied by the Belgians. And the copper cobalt flora, as it's referred to, is of extreme interest. And we have tested again for accumulator plants, hyperaccumulators. There's been some some equivocal information, which some plants did show very high uptake of copper and some of cobalt, but most are just very tolerant. So sadly, we haven't found many plants which would do the right thing on those types of soils. It's a pity, because the interest, I think, is there because of the unique vegetation. And I think it is more at that level that the mining companies have been recognizing this more in terms of restoring the native vegetation on the areas they've mined. So revegetation or restoration of the land with these native plants. And again, there's been a lot of projects, I think, run jointly with academic institutions by the mining companies to see processes whereby they can re-establish some of these unique plants. I have to say, though, that a large number have been lost. They have gone completely because they only occurred in one or two places, and the mining company's taken the whole hill or whatever, and that's it. The whole lot's gone. So the biodiversity interest is the main driver there, not so much the ability to take up the metals.
And how much of these hyperaccumulators do you estimate have been documented so far? How much remains left to be found?
You see, I always used to say we were looking at the peak of an iceberg, and I think that's correct. Although we've had this rapid increase in number simply in the last years because of the new instrumentation we've got to be able to find these. I do believe that I think for every element in the periodic table of elements, there will be hyperaccumulators. And that is my belief. I don't think I'll live long enough to see that prediction come true, but we're finding more and more. And of course, the interest now is in rare elements because of their unique electronic properties, which are being used clearly in the computer industry and so on. And I think we will always find that there is going to be a biological accumulator of metals. Whether it's economic then to grow those and extract from those is a debatable point, but it may well be. They're not the easiest things to extract or to separate chemically. And if this can be done biologically or in conjunction with more biotechnological processes, that may be on.
So that may genuinely be an area in which agromining and phytomining might displace the more traditional methods of...
I think so, yes.
Okay.
I think, well, I would like to say they go run alongside, if not displace. Yes, I think so. And because the demand is great. Yeah.
And if you could venture another estimate of how long you think before there is some kind of viable agromining, phytomining industry anywhere?
Well, there is already. And I say the work that's going on is a commercial operation in Malaysia. So that's probably the first. The same, I think, can apply in Indonesia. We've got exactly the same thing there. And political issues, again, are, I think, quite problematic. And I think the interest value is such within parts of Europe, again, with the mining of nickel, that we've got a real driver there. I think nickel still is the prime element for this process. There's no doubt about that, because of something like 2/3 of the plants we know as hyperaccumulators are hyperaccumulators of nickel. So for that reason alone, it's a driver. The other rarer elements, we know rather few plants. For thallium, for example, which is a very rare element and very toxic, we know only 2 hyperaccumulator plants at the moment.
And you mentioned political issues in various countries that are perhaps impediments. What kind of specific issues are getting in the way?
I think bureaucratic, perhaps, rather than political. It's very difficult to work in Indonesia, and that is more a bureaucratic problem, I think. I think, again, for mining companies, it's quite difficult for them to operate in some countries, which clearly that becomes political. In China, there's a lot of interest in this work, of course, and I think, again, we've found quite a number of hyperaccumulator plants in China, and I work with 2 universities there who are very interested in developing this, more, I think, for cleanup, than land cleanup, than commercial, except for the rare earth work is coming out of China, that's for sure. And that's where a lot of the rare earth elements are mined.
And apparently Afghanistan as well is likely to be another very major.
Well, I think there'll be major problems of working in Afghanistan, I think, and Iran.
To say the least. But could this potentially be viable there as well? Right.
Certainly. Yeah. I don't see why it wouldn't be viable anywhere if the wherewithal is and interest is allowed. I've worked with Iranians. Some of my students were from Iran, and I mention it there because there are vast areas of these nickel-rich soils in Iran, and we've found already unique plants there. So, but more like the European ones. They're
more Mediterranean.
Exactly, Eurasian Mediterranean plants. Yeah, but the tropics will always have the greatest diversity, and I think the greatest opportunities for discovery.
Well, what would you perhaps say to any either established or up and coming people in the mining industry who might be having their doubts about the viability of this? What would you say to try and encourage them to look at it more seriously?
Well, I would say look at what we've done, look at the production that we can offer, but not to compare it against traditional mining figures, if you like, but to see it, as I refer to it, as icing on the cake, and for a niche market, something different, and for cleanup of land that they've devastated, which is often the case, where you can extract from the materials which they would not be able to use for conventional mining operations. So again, the mine spoils, the wastes, and so on. This may be an opportunity of both restoring native vegetation and also at the same time extracting metals to improve the quality of the material that's left.
If I could come back to something that you mentioned previously, you said that these processes so far have shown to produce nickel of minerals in very high purity, more so than in traditional mining. What kind of specific industries would require minerals of that purity, and could they perhaps, like the phrase I'm thinking of is like a captive market, but maybe creating some kind of way to ensure that those specific needs are met by mining operations that use these processes?
Well, it's not really the mining industry that uses the processes. I think it's the industrial processes that have a demand for particular high purity. And they are, as I sort of mentioned, things like the glass making industries, things like, well, I mean, it sounds trivial, but jewelry industries and so on, things where the metals don't require to be mixed. Catalyst industry, for example, that's the other thing I haven't mentioned, but some of the materials that have come out of or been found in the ash of these plants when they're ashed at certain temperatures have very, very unique catalytic properties in the chemical industry. So this is something else that's come out. And we know a lot about this, about the nature of the ash and the way in which the metals are distributed in the ash. That material can have very unique properties. And those are things which are being looked at by other groups, because that's another beneficial effect that wouldn't come from a traditional mining source. These are materials which, because of the matrix in which the metals are presented, they have a very useful property.
Well, it's interesting that you mentioned like the jewelry and glass making industries
Yes.
are like artisanal kind of
Yes, exactly.
industries,
Yes.
because that would seem to create an opportunity for small and medium-sized enterprises
Exactly.
in countries like Australia, Britain, to
Yep.
specifically seek out metals obtained in that way and maybe certified that they came from Malaysia, for example.
And they are green sources,
Exactly.
and again, I'm not trivializing that, because I think that is becoming a label which is becoming very important. And
is that something on the horizon of labeling?
Yes, I think so. I think it's eco-labeling again, and it's rather like the nutraceutical side of things. And something we didn't mention, but also was a spin-off, was that in the case of zinc and selenium, which are trace elements that are required, obviously, in our diet, in all animal diets, sourcing materials that have come through the plants which accumulate those elements gives, again, a unique opportunity. These are bio-sourced materials, not materials that have been produced in the chemical industry. And that, I think, again, is a niche area. These are small on a global market scale, but we have a very good selection of plants now which will hyperaccumulate selenium. And similarly for zinc. Now, in fact, zinc was the first of the metals that we discovered which were being accumulated by some plants.
And where should people go to if they want to follow these developments more in depth? Like, where can they follow your work, for example?
The sources, I think, of information are inevitably academic sources, publications in journals, conferences. Certainly a lot of material is presented by all the relevant groups now around the world, and it is all around the world, by the way. I mean, it's become very much a global interest. And also, we produced a book on agromining, which has now gone into a second edition. There had been such enthusiasm for it that this was the state of the art. And I won't do a publicity drive on this, but if anybody was interested, I'm sure we'd be able to give a source. It is a collection of summarized materials by all the groups that are around the world that are working in this area. And it's called Agromining, Farming for Metals. So I think that gives you the background, and it gives you all the interest value. It gives you the history of the works. And that's as far as I'll go with the advertising. Well, I think that if you like, the take-home messages are that this is still a developing technology, and it has been for a long time. It's come up and down in interest, but the global interest now is high. There is a lot of interest from the mining industry, for sure, because they see this as a bonus. And obviously, it's very good for them to be working in this more greener environment. I also would want to stress that this is not magic. We're understanding the processes a lot more and how to optimize these processes. And I think we'll be learning more and more about that. One thing that I didn't mention is that what we've recognized now, I think it's not just the soil and the plant. It is what we call the rhizosphere, the root zone around the plant, and the microbial component of that, and the role that plays in the whole process. So the system is plant, soil, microbes, very much involved in the game, and optimizing all of those aspects, I think, and even changing the properties of the soil. We haven't mentioned that, but we can make the metals more available to the plant, and that's another way. Okay, it's involving bringing materials in, but it may be of economic benefit to do that.
So once again, Professor Alan Baker, thank you very much for discussing this very exciting development, and one that I'm sure many people will continue to follow as it develops further.
Thank you very much.